Hi guys, I'm Casey. Working on the ST20Y. A little bit about me. I'm from Portage, Indiana. Lived in Indiana almost all my life. I heard about the Geek Group through a video by Boden on the Captain's blog for a review of the Volcano Inferno, and I've been kind of following them ever since. I'm really interested in the CNC shop, and I'm working on a project, a prototype for an electronic cigarette, and I saw that they were getting some much better equipment than the TL and the TM, and decided to make my way up here and start my project. I'm self-taught in CNC. I've got a hobby grade machine at home. I had that for about 2 years, and came up here to learn how to use something more professional. So right now I am changing some tools around. I'm going to be putting this drill into this VDI slot right here. So I've got to remove the turret plug first, and then put the new tool in. I'm going to try and get a camera angle on it so you can see what's going on. So that's it. That's really how simple it is. Hopefully you caught that on video. Not sure. I'll be back later. Alright, so now that we got the tool in the machine, I'm going to go ahead and probe it. Go to MDI, Program Conversational, and up to the probe section. It's in manual mode. Tool number is 3, the offset number is 3, and the tip direction, which you can see right there, is 7, which means that it is an axial drill. You can also change it to 8 if you want to probe the x-axis instead of the z, but you'll then have to add in the diameter of the drill. All of the x offsets on this machine are in diameter mode. So to lower the probe, press F1.
Our metalworking shop, we have a full CNC machine shop with
and it brings the tool probe down.
VF2 milling machine, which has
go ahead and
there's only 3 in it right now. We've got the other 2.
Jog Z-axis over. This particular drill is extremely long, so we have to be very careful about clearance on the tailstock from the back of the turret.
Most lathes that you're used to, the lathe has a chuck that spins the work, and you move like this and this, right? Well, this lathe can do this, and this, and this, and this. Normally with a lathe, it'd be really easy with a lathe to put that dimple in the middle and spin it. You can only put it on the table. This lathe, spin this like this.
So now that it's a little closer than a 1/4 inch to the probe face, we're going to go ahead and
you're going to run a cycle,
press cycle start. I'm probing the tool.
Probing? Okay.
Yeah.
He's probing. But with this machine...
So current offset for Z is right there, and we'll see if it changes.
With the threads and the flat head.
Can you, like, program something in AutoCAD for it to be made
draw a picture of it and get information. If you think that it's just file to print, you're in for a lot of pain. I know that. Okay. that part hurts. This is a VF2 milling machine. This holds the work.
So for some reason it's not working. I'm gonna come back to you in a minute. Alright, so it turns out the feed rate was set to 0, and the intuitive programming system needs a feed rate in order to do the probes. So go ahead and hit it now. Touches off course and then fine. And it looks like we actually did have a little bit of change. So this is why you probe off your tools when you put a new one in. Usually what I will do is probe every tool that I'm going to use for the day. You probably don't necessarily need to do that, but for safety purposes I definitely want to. So more as it happens. Now that I have the tools I'm going to use touched off, I'm setting Z0 on my stock using the ultra precise post-it note method. But I just wanted to turn this on to mention one thing that you need to know when working with a lathe with super long tools such as this drill. Now, I've already done this, but you need to make sure that you have clearance from the back wall when you're using other tools. You could run into a situation where you've got a tool such as our cutoff blade here, or our turning tool, which goes really close to the chuck, and you could actually wrap it into the back wall and punch a hole in it, break your tool, break the machine, and it's a really bad time. So yeah, that's some information for you. See ya. Something we haven't done yet, but it's supposed to be done every day, hadn't really thought too much about it, is grease the chuck. I use a special type of grease called Chuck Ease. It contains a lot of molybdenum disulfide, very slippery stuff. I'm familiar with that because I ride dirt bikes and we're supposed to avoid any oil with moly in it, because a modern dirt bike has a wet clutch, uses the crankcase oil to lubricate the clutch, and if you got moly in there, your clutch will slip, and you definitely don't want your clutch slipping. But you do want the jaws on your chuck to slip. So since we haven't done it, I'm going to put 3 good squirts in there. And then we'll get it all cleaned up, move the chuck a couple of times. Make sure it's in there. Wipe it off with a rag and we'll be ready to turn some parts. Mike and I made a change to the way the lathe does tool changes last night. And basically we use macros to have the machine interpret M6 as a macro. So anytime you put in an M6, it will run this program. And what this program does is puts it in rapid mode, stops the spindle, rapids the X first into machine 0, and then the Z into machine 0. So all tool changes happen in this position, as far away as you can be from the chuck. Otherwise, as I unfortunately found out, you can do a tool change right there. So for safety purposes, we wanted to try and add something that would make the machine go to the safest position before doing a tool change. And so that's what this program does. So this is the part that I've been working on here last couple of days. It's a tank for my e-cig. Liquid goes inside of here, just underneath the atomizing section, gets wicked up to be heated by Canthal coil. The captain's gonna give me a little crap about surface finish. It's not spectacular, but I don't really care because this is one of my finished parts. You can kind of see it. It's really a matte finish. We put it through a tumbling process, use ceramic beads in a cement mixer basically. We're trying for, rather than a super shiny, easily scratches thumbprint magnet, we went with a matte finish. And I like the way it looks, so we don't have to worry too much about surface finish. And yeah, something interesting that didn't really think about with greasing the chuck is that everything is now covered in grease. So I'll have to wipe that down. Probably put less grease in next time and wipe it down a little bit better before spinning it up. I'm going to try and run the program I've been running without coolant and kind of talk you through it. So the first thing it does is it changes tool 12 rapids toward the chuck, and this is where I index the stock. I release the chuck, pull the stock up to the cutoff tool, and that gives me my Z0. We do a facing operation to get exactly on 0, but this is pretty close. Goes back and grabs tool number 1, does that facing operation. It's a roughing pass and then a finishing pass. Goes back and grabs the drill. Just plows right into it. 1.25 inches in and out. Comes back and gets tool number 1 again to do the outside diameter. This does 3 passes, 30,000ths depth to cut. Finishes to 0.860. You can see that it's always going back to that 0 position for tool changes. This is a boring bar. It's going to do 2 passes from the diameter of that previous drill out to 3/4 of an inch. And then since it's a thin wall part, we're just using a grooving tool to cut it off rather than the full boring bar. The grooving tool is smaller in diameter, or smaller in width than the cutoff tool, so it saves me just a few thousandths of stock, and over 100 to 300 parts that'll all add up to a little bit of cost savings on stock. So that is the program I'm working on. We're going to set up for the third part of 12 and hopefully get that proved out today. I don't have the correct stock, but we do have some what looks like 2024 aluminum, and we'll go ahead and use that to prove out the code. I got this stuff right here. So that's my day for today. If we get anything else interesting, I'll let you know. If you've watched any CNC videos, you're probably used to seeing chips that look something like that. You know, they're tiny, they fall on the floor really easy. What you're probably not used to seeing is that. And that is one of the chips that comes off of that big 709,000ths drill on an 1.25 inch, just balls out cut. I find it pretty darn cool. It's really thick. We're taking 6 thousandths per revolution feed rate. That means that the Z moves forward 6 thousandths every time the spindle makes one revolution. Pretty neat. So I wanted to talk for a minute about how machine and tool offsets are different in a lathe than on a mill. This is the tool offset screen for the ST20Y, and as you can see at the bottom here, when they're highlighted, the axes are currently in their 0 position. You have X, Y, Z, B is the tailstock, and C is the rotary motor for the spindle itself. It's a different motor from the spindle motor, and it has to be engaged with an M code, but it has the same sort of resolution that all the servo motors on the axes have. So let's look at tool number 1 here. You see the X offset is 10.6063 inches from machine 0 to the spindle center line. So from this point right here, machine 0 in X, it's 10 inches and a bit of change in diameter mode. So that's different from the mill. It's not actually currently 10 inches from the center of the spindle, but if you're making a round part, you're going 10 inches in diameter to get to spindle 0. Z is pretty much the same as on a mill. It actually is almost 12 inches from its work offset. When the probe comes down, it's actually measuring the offset from the probe location, and the machine knows where in space the probe is. And then you touch off using Z face measure to get your G54 Z offset, and ours is 4.5 pretty much. So yeah, that's how it's different from the mill. We're not going in exactly inch for inch in the X. It goes off a diameter position to where I'm going to need them to be. Alright? So I'm going to go ahead and move the jaws on their serrated edges for the next part that I'm going to be doing. The last part used 1-inch stock, and this uses 1/2-inch stock. I figured out yesterday that each serration on the jaw is equal to about 1/8 of an inch. So I'm going to move it in for serrations. Alright, so that should be it. Just get them snug so I can test fit it, and then I'll come back and torque them afterwards. So that's how you adjust the jaws.
Cool.
So I've tightened down the jaws, test fit already. They're torqued down now. And this is our 1/2-inch stock that we're going to be using today to do some code testing, and it works like a charm. Let's find jaw number 1 here. On the jaws, it may be very difficult to see, but there is a little window that shows you the stroke of the chuck, and it needs to be centered in the window, and so that's how we figured out that every serration is about 1/8 of an inch in diameter. So yeah, there we go. Before I even run air, I like to run through all the code that I've made and check to make sure it doesn't do anything funny. You really have to know your G-code pretty well in order to see it in the code. But I'll run through a couple of lines with you. This is the program name. That's what it saves to on memory. It's always an O followed by 5 numbers. As a man-readable, it just gives it a name outside of the program. I put in a man-readable that tells me what each operation does. So in this case, we're indexing the stock to T number 12. This is our macro M6, which makes sure we're home prior to a tool change. This is our tool number with the offset number. Especially with the lathe, you want to have the offset number, and especially with a Y-axis lathe, because it is possible to have multiple tools in the same station. G54 is our work coordinate. M5, I'm just making absolutely sure that the spindle is off because I'm going to be putting my hand in the machine. We rapid from home to 1 inch from the face of the part. Rapid in X down to the center line. Rapid again to where I want the stock to hit. I put in 2 mandatory stops. It's probably something you haven't really seen yet. M00 is a mandatory stop as opposed to M01, which is an optional stop. The program will stop and wait for you to do something with an M0. Put it in twice just in case I accidentally hit cycle start. Once the stock is indexed, we move it away to clear it by 1 inch. Then this is a clearance move, and it's going to clear again after that. I just like to be extra safe. We have an optional stop here. If we're running with the optional stop button activated, it'll wait for you to press cycle start before moving on. Our first operation is going to be a facing operation, which we're going to take the face of the part down from the Z.02 to 0. So our M6 macro, we're going to be using tool number 1, which is an OD turning tool with through coolant. Work coordinate. G50 is a maximum spindle speed. We want to limit the speed of the spindle to 2,500 RPM. It will do 4,000, but we'd like to keep it from going that fast. G96 is constant surface speed. We're trying to match the material at 1,000 surface feet per minute and 3 spindle forward. M8, turn on the coolant. From here, I found a mistake in the code. I need to rapid in Z first, so I'll go ahead and change that when I'm done vlogging here. We rapid to the outside of the part on the X, and 2/50 thousandths away on Z. G72 is a facing can cycle, picks up at N101, quits at N102. These are incremental moves, which are both zeros, no incremental moves. Depth of cut's going to be 30 thousandths, and we're going to use 6 thousandths per revolution. So these are the readables that the can cycle picks up from. And then we go to OD turn. So I'll go through this through the entire program. Just make sure there's no funny stuff like what I saw and have to change. And just make sure it's safe before cutting it in air at slow speeds. And after that, we'll do a slow feed run with metal. And once that program is proved out, then we go full speed. So what are we up to, Batman?
We are cutting on some diamond plates.
I'm going to get on the other side of the grinder.
That'd be a good idea.
Oh, I started to drift a little.
Drifting.
See, that's why I like the tape, though. I can see that a little better than...
Yep. Cool. Yeah, that's way better than bandsaw, jigsaw.
Right.
Yeah, those diamonds will just move that blade all over the place, you know?
Yeah.
Cool. Alright, so I've finished looking through my program, fixing any errors, and I went ahead and did an error pass just to check it. You know, you really got to pay attention, so I didn't want to take video of that while I was doing it for the first time. I'll go ahead and do it at full speeds and feeds with only a 25% rapid, so you can see what the new program is going to look like. Always want to do an air pass before putting metal stock in, just to make sure it doesn't do anything funny. I'm not 100% sure that my chamfer is going to work, and I won't know until I put stock in and just test it. So I'm going in single block now. You want to do your air test in single block so you get time to stop it. I normally go with 5% rapids, but like I said, I've already done an air pass on this at 5% rapids. So like the previous program, this is an index of the stock. And you can see that our macro pops up when we get to an M6. So I already did a clearance, but I want to make sure my tool change is at the home position. And see my green light is flashing, it means it wants operator input. So my first bit of OD turning is done. On this particular part we have two different facets at two different diameters, so I put in a rough turning, a can cycle, and then I'll put in a second rough turning can cycle, which start right about now. So that cycle's done. This is the chamfer, and I'm I'm not entirely sure that it's working the way I want it to. Doesn't seem like it's doing the pass exactly the way I like it. It may be just doing steps. It may be terracing the stock first and then doing the chamfer afterwards, so we'll have to see when that goes to metal. So now we're putting in a OD grooving tool. And this is for an O-ring landing. And the final operation is with our cutoff tool. And that's the end of the program. So the program is proved out. First part is off the lathe, and it turned out exactly the way I wanted it to. That chamfer worked like I thought. It terraced first and then did the chamfer. Took dimensions on it, and everything is exactly the way it's supposed to be. So now that the program is proved out, I can go ahead and turn everything up and just let it run. Since this part is so tiny, the screw tool coolant is just spraying all over the window. I may hold it after the turning is done and just pause video here and wipe the window down so you can see. Alright, we're back. And a program. Another one done. This one takes, well, it took a little longer because I had to pause it, but about a minute. So Moose has some carvings here at looks like plexi, and wanted to put a bit of a route on it, and looks like the router just melted the plastic. So Aaron and I put together a setup so we can screw it down to the mill, so we can, you know, change the speeds and feeds on there and hopefully get the plastic off without melting it. So that's essentially my day. Got a part prototyped. We'll get it done in the correct material when I come back next week. Got a bit of a drive home, so I'm going to be leaving here soon. I just want to talk a little bit about what you might expect if you're coming to the CNC shop for the first time. When I got here, I had a year and a half of experience on a hobby grade lathe. I had a fundamental understanding of G-code and machining practices. This isn't like a college campus. There's not classes and courses. If you come here expecting to learn everything from scratch, you could do that mostly on your own, and you'll ask questions and they'll be answered, but it's going to take you a very long time. You have to have some basic understanding. My recommendation is to start with some cheapo manual machines. You know, Harbor Freight has some for not all that much money compared to some of the other equipment. But if you come in with a firm understanding of how CNC works, knowledge of G-code, knowledge of speeds and feeds, you'll be set. You'll be in a good position to transition that knowledge from a hobby grade machine to a professional grade machine. The house control is really easy to use, but you're going to need to spend some time figuring it out. And when you get stuck, Moose or Mike can definitely help you. So yeah, that's the end of my blog.